So one of the predominantly used clustering method is hierarchical clustering. Hierarchical clustering. So it creates clusters that have a predetermined order top to bottom. There is a predetermined order from top to bottom. Hierarchical clustering. So in hierarchical clustering, the output will be a dendrogram. This is called a dendrogram. The output will be a dendrogram. In hierarchical clustering, the output is a tree-like model. We call it as dendrogram. You can see here, you will get a dendrogram like this. This is one cluster. This is one cluster. So the output of hierarchical clustering is a dendrogram. Okay. So the output will be like this. You'll get a diagram which will give you the clusters. Now, like you see, there are two methods. Divisive, where or top-down method, all observations are assigned to a single cluster initially and then partition least similar clusters using a flat cluster. In agglomerative method, also called as bottom-up clustering, all observations are assigned to its own cluster and based on similarity, clusters will be formed. So divisive is top-down method, agglomerative is bottom-up method. Most used is agglomerative. And by default in R and Python, it is agglomerative. So agglomerative is used in text mining and natural language processing. Hierarchical clustering has better performance than k-means clustering. You can also use k-means clustering for grouping the words. Hierarchical clustering has a better performance and it is widely used in text mining and natural language. When you look at hierarchical clustering, the distance method between the clusters is slightly different. The three distance methods for intercluster. In k-means, it is intracluster. Got it? In k-means, it is intracluster because in a cluster, you have a midpoint or a centroid and you measure the distance from there. That is intracluster, within the cluster. Here it is intercluster. Between the, so the intercluster distance methods are single linkage. So single linkage, as you can see, this is the formula. What do you observe? Minimum distance between the two closest points of the cluster. These are two different clusters. R and S are two different clusters. It is measuring the minimum distance between the two closest clusters. Minimum points. That's what LRS is equal to min of distance XRI XSJ. This is single. Then comes your complete linkage. Complete linkage, where we find the max distance. Opposite to single linkage is complete linkage. Here we are finding the distance between the max distance between the two observations. Complete is max, the farthest points. And the third one is the average. As it suggests, you calculate the average of distance between the points. We'll calculate the average between each of the points and we'll take it. So single, complete and average. By default is single. And here also Euclidean distance is used. Got it, guys? Any doubts? Okay, we'll go forward. Now all of you can open yesterday's Excel sheet or you can create a new sheet, no problem. Okay, so let's say I have a distance matrix between these points A, E, and F, 0.71. This is an Euclidean distance matrix. Already we have calculated the distances. This is an Euclidean distance matrix, 5.66, 3.61, 4.24, 3.20, 4.95, 2.92, 3.54, 2.50. This is 2.24, 1.41, 2.50. This is 0.50. This is 1.12. Now in the empty cells, you will have the same values in the empty cells. This is an Euclidean distance matrix and we will be using single linkage. Now in the whole of the matrix, what is the minimum distance? Minimum distance is between, which is 0.50. The minimum distance is 0.50 in the whole of the matrix, which is between D and F, D and F. That means the first cluster that will be combined is D and F. The first cluster which will be combined is D and F. So the new formation would be comma F and E. Similarly, A, B, B, comma F and E. Between itself is 0. Now, these values remain same. A to B, 0.71 will be same. This will be 5.66 and E would be 4.24. This would be 4.95. This would be 3.54. Between C and this 1.41. This would be, okay. Now we have to calculate these empty distances. Okay. So we have to update this matrix with the calculation because we have combined DF into first cluster, right? Now we have to calculate distance between D comma F, which is the cluster, which will be min of distance between DA and FA. What is the minimum? Which is, what is distance between D and A in the original matrix? DA is 3.61, 3.20. Sorry, FA is 3.61 and 3.20. What is the minimum value? 3.20. Minimum is 3. So you will put here 3.20. Similarly, to B, which is DB. So min of 0.71, right? DB. No. 2.92. 2.92, comma, FB is 2.50, right? 2.50. So the min is 2.50. So you will put here 2.50. The next one is DF2, min of DC, FC. DC and FC. DC is how much? 2.24, right? And 2.50. This would be 2.24. So we will put here 2.24. The last one is, which is DE and FE. And 1.1, it will be 1. So you will update here as 1.00. So this is the new updated. Now in this matrix, what is the lowest one? In this whole matrix, the lowest is 0.71, which is between cluster A and B. Cluster A and B. So we have to update the clusters again. A comma B, C, D comma F. Similarly, A comma B. Madam, good morning. Where is the class run out on 1 work? Clearly, now 1 work class in 0 and 0. Now we have to calculate. No? Yeah. Minimum, na? The minimum in the matrix. What is the lowest in the whole matrix? Because this is what point of D and F. What is this point? Intersection of D and intersection, na? Matrix. Intersection of D and F is 0.50. This is the intersection point. No. Whatever is the lowest value in the whole matrix, what is the lowest value? Here it is only 0.5 is the lowest. It can be any lowest values. It depends on the distance. This is a distance matrix. The distance have been calculated using the Euclidean distance formula. Okay. So the lowest distance is between point D and point F, 0.50. And we have merged them into one cluster. And we are calculating that distance with other clusters. So 2.24, 1.41 and 1. Old cluster values. So we have to calculate these 3 values. We have to calculate these 3 cluster values. So distance of to C, AC is 5.66, BC is 4.95. 5.66, 4.95. Right? 4.6 and 5.66 and 4.95. AC, BC. What is the lowest? 4.95. Similarly, we have to calculate the distance between, this would be 4.95. Now, this is a larger calculation we have to do. Distance between D comma F. As per the formula we are going. Okay, why it is not going? Why it is going like this? So minimum of DA, DB, FA and FB. So if you go to the original matrix, 3.61, 2.92, 3.20, 2.50. The minimum of all these things, what is the lowest value? 2.50. So this will be 2.5. Then min of AB2, E. AE, B, E. AE is 4.24, D is 5.4. So what is the lowest value? 5.4. So we will fill this with 3.54. This is the updated matrix. Now what is the lowest? The lowest value is 1. That means we will be merging DF with E. The merging will be DF with E. DF is one cluster merged with E. This is A comma B. So same thing, Control C, transpose. Okay, this is 0, this is 0, this is 0. So AB to C is 4.95. We have to calculate the other two. No, this also is there, no? DF, no. DF to AB is 2.50, right? Or no, we have to calculate, right? Distance between D comma F, AB, sorry. First we'll calculate for AB. So we are calculating this point. So DA, DB, FA, FB, EA, EB. So the mean of the distance is mean of 3.61, 2.92, 3.20, 2.50, 4.24, 3.54, 2.50. This would be 2.50. Then DFE to C, min of DC, min of, which is min of 2.24, 2.50, comma 1 point, and the min is 1.41. So we will fill this as 1.41. Now the lowest is 1.41. So DFE and C. So A comma B, and now first D comma F comma E comma C. This is 2 point. If you take the min of all DA, DB, FA, FB, EA, EB, 3 point, I think same thing, 5.66, comma 4 point. So the lowest is 2.50, A comma B. Now we will start merging the clusters based on the distance. So what is the first cluster? And F. The first cluster is D and F. The next cluster is E, right? Then the next cluster is, then the final outward cluster is, and if you are looking at it, the distance between D and F is how much? 0.71 is distance between A and B. So the distance between D and F is 0.5, A and B is 0.7, DF and E is 1, and DF, E and C is 2.50. So this is called dendrogram. So this is the cluster dendrogram, which we will get after doing the clustering analysis. This is your cluster dendrogram, a tree-like structure where you have the grouping of clusters based on the. So this is the process of hierarchical clustering using single linkage. If you are using complete, you have to take max. Instead of min, we will take it as max. In average link, you have to calculate average of all the, that is a little bit complex calculation. Single and complete are easy to calculate. By default is single. How the hierarchical clustering works. So this is how the hierarchical clustering works. Yes, single is default. Most of the times we use single only. If single doesn't work, then we go to complete. Single is the preferred thing. If single doesn't work, then we go to complete. If complete does not work, we'll go to average. Cluster formation is not correct. If you feel the clusters grouping is wrong or wrong, observations are being classified into wrong clusters, then we have to rework our cluster strategy. So we have to understand the clustering method. After getting the output, we should see whether they are being properly done or not. So that is, then again you can choose your choice. If two values are same thing, you can choose your own. If there are multiple cells with common distance, it's your judgmental call. But that very rarely happens. In real-time data, Euclidean distance of 2 points may not be same. Textbook data, you will have that scenario. But in real time, we don't have that scenario, right? So in yesterday's data, where all of you can open yesterday's notebook and run all the cells. Please open yesterday's notebook and run all the cells where we have done the k-means clustering dot cluster dot hierarchy. Or we will do one thing because we have to import other functions also. Import scipy dot hierarchy as SCH. Here we have to import multiple functions, so we can use the SCH thing. Dendrogram is equal to SCH dot dendrogram, SCH dot linkage of mol data, comma method is equal to you can see 5 clusters being formed, right? No, not more than 1, 3. 3 clusters being formed. Actually, these are 3 clusters, 2 and 3. This is 1 cluster, no? Second cluster. This is third. This is 4th cluster. This is 5th cluster. C, D, E, and this is like C, D, E, the other one extra, and then this is your A and B. In the earlier instance, when you're looking at your previous instance, these are 3 clusters. This is 1 cluster. This is the second cluster. This is the third cluster. And this is the 4th cluster. And this is the 5th cluster. 5 clusters have been formed. Dendro, DRO, spelling mistake. Check the spelling. SCH.DEN tab. SCH.DEN. This is name. There we have assigned a name to it. This is the name we have given. On the left side, we have given a name. The right side is the function. No, methods are there. What is different distance method? Linking method. So single, complete, average, weighted, centroid, median. There are different linkages. Single, complete, average, weighted, centroid, and WOD. So this is the formula for WOD. WOD variance minimization algorithm. So WOD is a little bit complex thing which we use. Again, WOD is also used in natural language processing. Text mining, WOD is preferred method. This is the formula for WOD. Okay. Now we also have in sklearn. Sklearn agglomerative clustering. HC is equal to agglomerative clustering underscore clusters is equal to 5, comma, affinity is equal to Euclidean, linkage is equal to what? Y underscore HC is equal to HC dot fit underscore predict, mall data. So for agglomerative clustering, we don't have dendrogram plotting. We'll get the cluster labels. So why not predict, fit only. Labels will get. Which observation belongs to which cluster we'll get. So dendrogram plotting, you have to use scipy.cluster. For agglomerative clustering, we don't have the plotting of dendrogram. But it will plot the dendrogram in the backend. Then only it will come to know the labels. Okay, all of you got this? One other clustering technique, which is very popular and powerful, is DBSCAN, density-based data clustering. To cluster data points, algorithm, high density regions, low density, DBSCAN, the specification of number of clusters. So you don't need to specify the number of clusters in DBSCAN. It automatically does. DBSCAN, distance calculated, Euclidean, DBSCAN, good at the outliers. DBSCAN, 2 parameters. The first one, epsilon, least distance to be termed. So what would be the distance required to consider 2 points as closest to one another or 2 closest to min points? Minimum number of points, a cluster. A cluster is recognized if the number of is greater or equal to minimum points. So density-based clustering technique, in the output, you will get 3 types of data points. 3 types of data points. The first one is 2 parameters, any data point that is not a core, min points. Okay, मैं अभी call करता हूँ आपको, ठीक है? मैं देखता हूँ. So this is the definition of border point, core point, and noise. Noise are typically outliers. Noise are typically outliers. They are not classified. Core points are the center points of the cluster, which are well defined. And border points are away from the core point. They are close to the. So you will get these type of data points when you look at the DBSCAN: core point, border point, and noise point. These are the definitions of the 3 different points within the DBSCAN. Right. Now, if you are looking at your DBSCAN algorithm, so this is the algorithm. Select the object from the set of match all reachable points from the selected item. If applicable, the epsilon. E is epsilon. Neighborhood contains at least minimum points, will form a new cluster. Find objects directly reachable from these cores, maybe joining clusters. Seize at the moment when none of the remaining objects can no longer be added to any clusters. So once there is no change in the cluster formation, the cluster algorithm will stop. So this is the steps involved in the DBSCAN algorithm. So density-based scanning, density-based clustering or DBSCAN is a very popular algorithm which is used in large-scale data. When you're dealing with large-scale data, this is one of the preferred clustering algorithm, and it's a non-parametric algorithm. What is a non-parametric algorithm? Non-parametric algorithm means no assumptions. Parametric means there are assumptions which are compulsory to be met. The assumptions have to be met. So when you don't have any assumptions to be met, then it becomes a non-parametric algorithm. Tree-based models are non-parametric. KNN is a non-parametric algorithm. Similarly, clustering techniques are non-parametric algorithm. So we'll implement this data algorithm, or we'll do one thing, we'll take a break and then we'll come and implement, because the process involves multiple steps. So we'll take a break for 15 minutes and then we'll come back and then we'll implement the algorithm. So guys, take a break for 15 minutes and then we will. So if the data set more than 2 dimensions, the min sample data dimension or number of variables. So 2 into dimensions. Dimensions means variables. That should be the minimum points per cluster. To calculate nearest neighbors, so from sklearn dot neighbors. So nearest neighbors, we're calculating the distance between the closest. You have to give neighbors now. Grouping. How many neighbors you have to? 3 groups or 3 neighbors. Yesterday I told you now, for neighbors you need to have a dependent variable. For clusters you don't need to have a dependent variable. But we are using nearest neighbors is just to calculate the distance between 2. We are not using the K algorithm. Nearest neighbors is a function to calculate the distance. Unsupervised learner for implementing neighbor searches. Default is Minkowski. Default is Minkowski's distance. Absolute. So it uses distance calculation of Minkowski. Generally we use Euclidean. For nearest neighbors we use Minkowski. You can change it to anything. You can change it to Euclidean also. See, city block, cosine, Euclidean, Haversine, L1, L2, Manhattan, non-Euclidean. You can give any distance measures. So 1, 2, 3, 4, 5 we have the maximum curvature. Maximum change is happening at 1.73. 1 to 1.73. Rest of all are small changes. 1 to 1.73 maximum change is happening. This is the maximum change, right? Which is happening at 1.73, which is 1, 0, 1, 2, 3, 4 is the point at which you have the maximum curvature change. So we will take epsilon as the point where we have the maximum curvature and min points. So how many variables we have? 4 variables, right? No, 1, 2, 3, 4, 5. 5 variables are there. So min point is 10. See, first point. The first change which is happening is what we are bothered about, not the last one. Here also, this is the not of significance. We have to look at the change that is happening around here. The first point at which we see the biggest change, which is around 4 or 5. From sklearn dot cluster, DBS is equal to DBSCAN, EPS is equal to 4, min underscore samples is equal to 10, dot fit small data. Labels is equal to DBS dot PLT dot scatter small data. You have done the screen, right? You got everything is blue, huh? Epsilon 8 and min samples 4, we are getting the. So these are the core, these are the border, these are all blue are all noise. This is the core, border, and noise. No, we have to specify epsilon and min points. Epsilon and min point has to be specified. I think automatic values are there. Min samples is 5, EPS is 0.5. Min points is number of dimensions into 2. But if you take it, it's not giving us the cluster. All of them are treated as noise. So I have reduced it to 5, which is a default. Default is 5, right? So we reduced it to 5. This is small data, no? That's why it is not fitting. DBSCAN uses large scale data. It needs very large data points. More than 10,000 observations with a minimum of 20 to 30 variables. Annual spending and, annual income and spending score. Annual income high, spending score high is this category, which is cluster. Cluster 3 has higher annual income, higher spending, second higher income and second spending score is this. Look at this cluster, they have higher income, but here they have lower income, but higher. Here, marginal. Both are same. So you can categorize the customers. These are the best set of customers. Cluster 3 customers have higher income, spending score. Next best is cluster 1, which also has 5549. Now this cluster, there is a problem. They have high income, but they are not. Here they have low income, but they are. So 0, 1, 2, 3. So in cluster 3, we have very few. Now this is problematic, right? Who has income and high spending is risky. We want people in cluster Cluster 0 is also preferable. Cluster 2, cluster 0 is preferable. Cluster 3, okay. Cluster 2 is okay. But we have to be careful with this cluster and this cluster. Okay. So you can categorize, give name, high income, low spending, low income, high spending. So that way you can categorize them into groups. We have to choose the variables which are important. In retail data, income and spending is important. Age is not much of a difference here, but age also you can add. This is these two high spending cluster is what? 32. Middle-aged, right? Middle-aged customers are high spending. Above middle-aged customers are not high spending, right? And young customers are taking risk. 25, na average age. Young customers are taking too much of, so you can add age also. Now it's your judgmental call, which ones you will take. It's purely dependent on your understanding of the data and domain data. So you can take only two variables, spending and income, or you can take age also along with it. And we'll ignore the gender because they're dummy variables. Again, we'll ignore the gender, male and female. That's for the time being, we'll ignore that. But look at the way using these three variables, you can categorize your customers. Young, risky customers who have low income but high, but the best is this. Middle-aged customers with high income and high spending. Got that clarified, right? So what you choose, take for example, I want you to work on this data. This is also live data, original data, San Francisco air passenger statistic. So where is the dataset download? Oh, we have to contact the dataset owner. Huh? Okay, earlier it was free only. So it has these variables: operating airline, WestJet, Virgin Atlantic, United Airlines, and then in geo codes and all. And then you have the passengers. Okay. So let us see where we can get the data from. Sport. Yeah, we got it. Yes, you can use. See, domain knowledge is required. See, sometimes we can't depend on algorithm only, right? We have to have domain knowledge. See, algorithms don't have domain knowledge. Now we have domain knowledge. That is why you are paid to understand. You have to learn. See, 2 weeks back, one of the students called up from Capgemini saying he is not able to understand the insurance data. You have to read the insurance articles and all. You have to understand what is mortality rate, what is the life to death ratio, death rate, fertility rate, all these things are there. Every city has death rate, how many people are dying, accident rates will be there, all this data will be there with the insurance companies, based on which they fix the premiums. So you have to understand the data. You have to understand the keywords and terms from Google articles. Nobody will help you. Here we have only one numeric variable, which is passenger count. We have only one numeric variable, which is passenger count. 24,968 observations are there. So you can cluster based on only one variable, which is, and you can take airlines, operating airline. So before that, we have to aggregate. We have to aggregate the airlines total by airline, and then we can use that data for clustering. So we'll do that. I'm sending the data. So only two variables will take, airline and passenger. Aggregate the data. First, total data of airlines. Then you can group the airlines based on passenger counts. If only categorical data is there, the clustering techniques, these techniques will not work. You need to have numerical data because distance cannot be calculated for categorical, right? Categorical or ordinal, they have, Hamming is text. No. Text. No. Hamming is not for categorical. Hamming is for text. No. Natural language processing. Movie names, movie titles, or words, sentences. That is what Hamming distance is. It is not for categorical data. Text data. Natural language processing means text, words, sentences, not keywords, words. Generally, we will take the paragraph. Generally, content will be in paragraphs. You break the paragraphs into sentences. Then we break the sentences into words, and then we process the words. Text mining is all about words. Sentiment analysis is all about sentences. Similarly, tweets, Facebook updates, WhatsApp chats, these are all text that will have emojis, all those things. No? So we have to clean all those things. We get the exact text of the exact content of the text, and then we break it into sentences, then do sentiment analysis, then we break the sentences to words, then we do word clouds, we do clustering analysis, we do all other algorithm based like logistic regression and all the things you can implement on the NLP. Text is different. Text is not categorical data. Text is completely different data. Text is unsupervised data. Text is also unsupervised data. So I've sent you the data set.